Hello everybody, welcome back to my first Petabyte scale architecture introduction. In the last session, we covered the introduction and we introduced many jargon that is relevant to build your petascale architecture. We discussed common issues and we discussed our 4 V's and generic big data architecture, and some implementation examples using AWS and GCP, and the differentiation of the databases which are relevant for our use case. We introduce the scale up versus scale out concept, decoupled architecture, fixed cost versus pay as you go, the knee problem, which causes your big data scalability issues, streaming versus batch, data warehouse versus lakehouse, type of databases, which are operational, analytical, and archive, type of storage, which is role-based or columnar. Here's an example of how the data is saved when it's columnar and when it's row-based. And we discussed about CPU concept and storage concepts and some file system and network concepts. And what I wanted to do today is go over some concepts as follows. Today we're going to talk about compression. To introduce compression, we're going to take by example AWS Athena, which essentially is a platform as a service. It's a serverless Presto-based analytical DB. Essentially, you pay as you go. For each terabyte scanned, you pay $5. Scanned means every data that was passed through Athena, you pay full. However, if the same data originally was compressed, then your scanning is essentially reduced by the compression ratio. Decoupled architecture, that means the compute is managed by AWS and the storage is managed by AWS S3. It connects well with the AWS ecosystem, and it uses external table instead of internal tables, so you don't need to do insert. Just put a file on S3, create an external table, and simply query it. The example here is what you see, 1 terabyte of uncompressed CSV file on S3, and when you scan it on Athena, you pay $5. However, if the same file is compressed using gzip, for example, and the compression ratio is 1:5, essentially, instead of 1 terabyte scanned, you scan 200 gigabytes, and the processing is the same, but you pay 20%. So this is massive cost reduction. So you can use Athena to do initial read, pay the $5, and then compress it back to S3. And for every subsequent query, you just pay the reduced fee for the same data. Should you always compress? Essentially, when you read compressed data, it goes to the RAM of Athena compute. You perform some decompressed compute, and then you process the data, and then you present it to the console. If you need to save it back to disk, so essentially another operation is applied of compression, and then you save it back to disk. However, there is a penalty when you have small files and decompress and compress time may be longer than the actual processing time, so you might not need to compress. Naturally, when the bigger the file size, the longer the process time. However, compression is meaningless in terms of the actual time. So why did we learn today? Performance has grave implications on performance and cost. And usually there are no simplicity issues if you stick to gzip. You can test other compression ratios if you want to have improved scanned ratio, meaning a smaller footprint on disk size. Let's talk about partitioning and the basic execution flow. One of the available storage formats is called Parquet instead of a CSV. Essentially, a columnar storage binary file that allows you to split the files. For example, the same amount of data with 10 columns. And when you want to read only one column out of T, and assuming evenly distributed storage, that means you pay 10% of the $5 or the $1, that depends on how you look at it. And that depends if it's compressed or not. So reading to Athena is essentially less time. Decompression and processing is much less time, simply because we apply the right storage format. If you apply on top of the storage format a partition, naturally you cut down even more. Assuming you have 1 terabyte with 10 columns, partition by date, you have only 10 days, meaning 10 partitions. So you cut down by another 90%, and you end up with 5% processing for specific day and specific column. What happens if you have too many partitions? Notice the year 2042. So essentially, you have a penalty of scanning the entire partitions and skipping them. So this could be a big data by itself, assuming partition by day. Because for each year you have 365, 20 years, then you have a couple of thousands of partitions. This eventually will end up slowing you even more. So what happens essentially if you have 100,000 partitions? So filtering the columns to read will take you much more time than actually reading the file, as I mentioned before. So the more partitions you have, the greater the penalty of reading your data. So one should consider carefully the amount of partitions per table. Putting your data to a test. Essentially, it all boils down to this framework of faster, cheaper, simpler. Every good architecture should be balanced in the middle, smack down in the middle. However, sometimes it's only 2 out of 3. Either it's fast and simple, but it's costly, or it's fast and cheap, but it's not simple. You have a big data problem when your system occasionally breaks. Occasionally could be once a day, once a week, once a month. But if it happens too much to your opinion, that means your infrastructure, your architecture is inaccurate. So the challenge of selecting a petascale architecture is that sometimes using scale-out architectures is not enough. The reason for that is because you end up generating a lot of data per machine. So assuming, let's draw something here, not here, over here. let's draw a scale out scenario where you have lots of servers. Okay, imagine this is server number 1, and this is, oops, got too excited here. Server number N. So essentially, when you process 1 petabyte, you need to divide your workload into this amount of servers. But at the end of the day, your cluster will be as powerful as your weakest node. Because what happens is, in reality, is that over time, you add more and more servers, but not always they are of uniform size. So eventually, even if they're all the same, all the data comes to one machine and it needs to be able to process the aggregated results of a single machine. So essentially, bottleneck is created. Let's see if we can draw a line here. Whoops. Let's insert a shape over here, make it more readable. Insert shape, arrows, yes. And here we go. Even if you're highly distributed, in the end of the day, there's one server that needs to respond with the correct answer. Okay, so this becomes your problematic bottleneck. So what's the challenge with scale-up architecture? Essentially, if we take a server and we make it bigger, you might end up in a scenario where you get stuck. And why is that? Because, one second, let me draw this arrow over here. Insert shape. Boom. Right. Insert shape. Thank you. Over here. So this is server before scale up, and this is server after server after scale up. So it doesn't matter how powerful this machine is, eventually you will end up in a scenario where you have a power query hitting too much data for one machine to handle. But in today's world, there could be massive amount of compute power per one server. In the past, that was a problem, and all servers had much less compute power per machine. But today, you can have massive amount of CPU and RAM and storage per one machine, so it becomes more and more sensible to dense your cluster as much as possible in some cases. So let's assume you have many small machines, say 10 machines of 4 CPUs. Okay, for example, you can take for extra large, which is a bit different for CPUs, but it doesn't really matter. The hint is that if you go to the instance of AWS spec and have a look at RA6 memory optimized machines, RA6 over here. You see that you have dedicated network bandwidth per machine. So you see here, over here it's up to 12.5 gigabits, and here it's dedicated 12.5. And when you scale up to the next level, you get much more bandwidth per machine. Actually more CPU and memory, however, the bandwidth is sometimes overlooked. So this is essentially problem number one. Problem number two is when you have two machines which are more dense because you increased your network, so your bottleneck becomes the throughput you can generate from S3 and parallelism. For example, here you get more parallelism because you have more machines, so you get at least 4 parallelism, but here you get only 2 parallelism. So essentially it is always a benefit of having more machines or less machines, but in a sense, I would rather have 2 powerful machines than 4 which are weaker, because I want to guarantee maximum throughput, and I assume the compute will be enough to handle. So what happens if you have 2 machines of very powerful CPUs, for example, 64 CPUs for 16 extra large? As you see here, the 16 extra large compute memory optimized 16 extra large has 64 GPUs. The problem with these machines is that they are not always available for you. Meaning if you use transient cluster that goes up and down every now and then based on your workload, and you use port instances, AWS or another vendor who might say something like, try again later because there's no available machine, because these are the most commonly used machines. Any questions before I proceed to our use case? Thank you. Okay, so let's talk about today's class. It's about the 1 petabyte use case of sensor data. Essentially, we have a 1 petabyte of weather sensors, and we need it to make it accessible for analytical purposes. It doesn't grow, it's static. It contains 1 table, it contains 5 columns, timestamp, geography ID, sensor ID, the value, and the actual value of the sensor and the sensor type. Data is located on the storage server on the data center, and all data is in CSV format. And the data is compressed in gzip, 200 terabyte after compression, 1 petabyte before compression. And 10 analytics users or analysts with a full-time job will be querying the data all day long. Assume 3 years worth of data. Frequency of sensors every 10 seconds, several sensors, and 7 geographies. For today's purpose, we are only going to evaluate and design the database, the technology, the compute, the performance, and some TCO analysis, total cost of ownership. The questions you should be asking yourself about the use case is about the output expectation. Are you expecting aggregated results or something else? For the purpose of this exercise, I answered as if I am the customer that it's aggregated results for a month. And the type of queries are joint, power queries, aggregations, and window functions. The performance target are flexible because it's for research purposes. Estimated budget, I don't know. Maybe less, maybe more. Give me some analysis and let's decide later. And the type of user is Power Analyst. And the format of the result is package gzip. This is given, you don't have to take care of this. So which technologies are we going to use for our following sessions? We're going to evaluate Databricks, Redshift, Snowflake, BigQuery, SQream, but we're not going to cover ClickHouse as someone suggested here from the chat. Okay, so let's talk about a real life use case. No, not a real life, a made up use case, which will resemble a real life use case. So we can build architectures around it in different technologies and take it from here. What do you say? Sounds like fun? Okay. So the use case details. Let's assume we have 1 petabyte worth of data. The use case is weather sensors, and we need to take data and make it accessible for analytics purposes. The data is not going anymore. It's static, 1 petabyte, and that's it. Essentially contained in one table containing 5 columns. Timestamp, Geo ID, which stands for geography. For example, Europe, Paris, or New York, US. Oops. Sensor ID, which stands for the amount of sensors you have, the value that was measured, and the type of the sensor. Data is located on the storage server on an on-premise data center, not cloud. All the data is in CSV format, and all the data is compressed, essentially taking up 200 terabytes after compression, and it's 1 petabyte before compression, just to be clear. Can anyone mute themselves? Good, I did that, great. So the use case here is 10 analytics users working full-time, and they will be querying the data all day long. Assuming in terms of historical value of the data, it's 3 years worth of data, frequency of sensors every 10 seconds, several sensors, several geographies. Essentially, you can choose your infrastructure and your ETL tool and how to load and how to design the database and so on and so forth. Currently, what we're going to do only for this discussion, because this is a very long discussion, is only design the database and compare several technologies and do TCO analysis just for the sake of fun and exercise, purely as a learning exercise. Any questions about this use case? Okay. So which questions do you think we should ask about this question, this use case, before we get started?
I think what kind of analytics use cases and kind of like time expectations, output expectations?
Okay, output expectations, type of queries, very good. Questions about the workload is always good to understand what you're about to tackle. Any more?
Time expectation, how quickly we want to get the result.
Performance
maybe also
target.
Maybe also cost if we want to keep under a budget.
Budget, very good. What else?
Maybe what would be the users? Are they data scientists or like
Analysts, as stated here.
yeah,
They are not.
okay.
They are not data scientists. Analysts. But let's
Okay.
type all users. Power analysts. And now let's I will answer this as as defined. I will simulate the answers for estimated budget. I don't know. I don't know. Performance target, flexible, research purposes. So process, we can wait some time, type of queries, joins, power queries, aggregations, window functions, which are statistical functions. Type of functions, aggregated, output expectation aggregated to result.
What about like timeliness, right? So like how close to real time the data should be available?
Performance target. This falls
It's
under
part of performance.
target.
Okay.
Yeah, and I'm saying flexible. As the customer, it could take minutes, hours. It's okay. It's research.
Yeah. Okay.
Also, is there a requirement about the format of the results? For example, can we just store into like a Parquet files, or it should be stored as like a maybe
yes,
some more...
I want this to be in line with the rest of my data platform, Parquet, gzip. I heard about this guy Omid from Big Data Demystified, and he says, you know what, use Parquet, use gzip as a rule of thumb if you are not sure. So let's stick with this one.
In some cases, some would store into like a cloud data warehouse, like a Snowflake or kind of thing. So that's just want to, that's not the requirement, right?
Can you repeat your comment, John?
Yes. I mean, sometimes people would store it into a data warehouse, like a cloud data warehouse, like a Snowflake, right? Or Redshift or something like that.
Yes, yes.
So that's not the case. Right. Okay.
That's not what?
That's not the case. That's not for this requirement.
No, the exercise is to choose between different technologies, and we'll choose several technologies and run with them. Okay?
Oh, okay. Yeah.
Okay. Which technologies are we going to use for this exercise? I've prepared several. We can compare and try several. So you want to throw a couple of names here?
Maybe I would say first maybe Spark, right? So
Spark, we'll try for that. Databricks. Okay. What else?
S3.
S3 is storage layer.
Yeah, that's
I'm talking. So what other data warehouse, data lake technology are you familiar with, which is for petascale?
I think when you decide what would be the storage, then what would be computing, right? So
once you choose the technology, the storage would be obvious.
So for technology, are you talking about like AWS or Azure or GCP?
Anywhere you like. Choose couple, please.
I think what you're saying, because this is necessarily cold data, so we could use data lake.
Yes, data lake.
Data lake is that's the storage, right? That's the
yes,
data.
But you need a compute layer.
Redshift.
So Redshift. What else?
Also, do we need is a requirement about the data cleansing stuff, transformation?
No,
just
simple,
directly
assume
load
everything's
into.
clean. Yeah.
Oh, okay.
Snowflake.
Snowflake. Thank you very much.
Snowflake.
Anything else?
Can we use Airflow for scheduling orchestration?
Sorry?
For orchestration, can we use orchestration tools?
Yeah. Yes, forget the orchestration for now. We'll focus only on the database for now. Okay, and I want to add another one, which is StreamDB, which is better scale. Okay, so essentially we have Databricks for Spark, we have Redshift, and Snowflake, BigQuery, and SQream. Very good. Thank you very much. Compute challenges.
Wrote in the chat that object storage like AWS S3 is also an option.
Yes, but you need
It's
someone to
for-
process the data.
How about
So
ClickHouse?
ClickHouse is an option, but since it's an open source, I'm not going to cover this on our session. So I'm going to cover these 5, which are commercially available solutions. Yes, they cost money, but essentially they are designed to solve your big data, your petascale architecture.
ClickHouse has a cloud.
How about Kinesis?
I know, but it's not on the top 5 cloud vendors.
Gotcha.
I mean, how about Kinesis?
Kinesis is a solution that helps you ingest data, but not to process 1 petabyte.
Oh, okay.
Okay, so let's move on. Compute challenges. So essentially, you need to know the difference between CPU and GPU, because CPU is your bottleneck in your architecture, and GPU is helpful to do massive parallel processing. There are technologies which are based on C++, essentially faster than Java. And sometimes there are technologies that use SQL faster than code, and sometimes the other way around. Some RAM limitations, remember scale up versus scale out, and the knee problems. These are the major issues you should be considering when you have a look at the technology. On the storage challenges, you need to choose your disk type carefully, whether it's flash or magnetic. If you have, you should choose that carefully, since you're using a very high volume use case. There might be cost associated with flash disk, so consider having magnetic disk for this use case. Another thing to consider when you have to process 1 petabyte, you need to have available disk space. You cannot have 1 petabyte disk space, store 1 petabyte and have 0 disk space, because the operating system needs an empty disk space, and your technology needs free disk space to process intermediate temporary calculation. So essentially, when you're designing a 1 petabyte architecture, you need at least 2 petabyte worth of data. This is something to consider. If you don't have any latency considerations, then it's okay. Just consider the throughput considerations for the performance targets. In terms of network challenges, again, consider the throughput if there's no latency issues. Compression challenges, if there's a sensitivity in the TCO analysis regarding the file saved on disk. So do some testing around compression, change the compression algorithm. Usually compress and decompress time is not an issue on this use case, but you should be aware of that. the storage type, that really depends on the type of data you have. In most cases, Colonel would be more than suffice. You can use open source formats like Parquet, Avro, or proprietary like Delta Lake by Databricks, each of which have their own advantages. If you're not familiar with this, go with Parquet, and you couldn't go wrong unless you really want to be more modern and advanced, and then you need to have more details about the use case, because each of which have pros and cons. In terms of cloud vendor, maybe you want to be agnostic, maybe not. I don't know. It depends on the use case. For today's discussion, in the next discussion, we're gonna ignore this requirement, if any, because we want to test out for the learning exercise several different technologies. Some of them are cloud vendor related, some are not, or more agnostic. The use case for 1 petabyte usually comes with lots of problems by itself. It comes when you divide the market, based on my experience as a consultant. And these are the top 5 use cases. You have problems where you collect so much data, and the data keeps changing in the structure. So this is schema evolution challenges. And you have some sort of batch processing, for example, for telco. And you have ad hoc analysis, like when the one use case we're talking about, with ad hoc analysis for research and AI. And you have joins on big data, which is also common for in telco and industrial 4.0 and IoT use cases. The most complex of all is the embedded BI on raw data. Imagine a Tableau or Click connected to a database with 1 petabyte with live connection. It's a challenging use cases to tackle, probably the most complex of them all. And sometimes there's multi-cloud is usually associated with this one. Okay, any questions about challenges before we drill down into some technologies?
On the compute slide, you mentioned the languages of C++ and Java. Why not
Yes.
Python though?
Let me put this here.
Yeah, or
What I
Scala.
wanted to say on Scala. What I wanted to say here that C++ is by order of magnitude faster than these technologies.
I think
So
it
essentially,
also
please.
garbage collection comes into the question here. C++ doesn't have garbage collection, whereas other ones have. Yeah.
And JVM tuning is well being accurate. So essentially, these are the challenges. Any questions before we move on? Okay, so let's talk about the first one. Whoopa, Redshift. Let's try to see what's the time. Almost 7. Are you with me? It's gonna be about 30 more minutes. I'll do about 15 minutes per, maybe more. About 30 minutes for Redshift. I hope you'll bear with me. We can stop in any time, by the way. Just talk to me. I'm here for you guys. We can add another session in the future if necessary. So let's start with the Redshift and take it from here. Okay, so essentially Redshift is a technology which is quite familiar. There's not much to say here because everybody knows this technology. If you don't, feel free to ask questions. This is the usual introduction to every subject. I skipped it because I didn't in the previous recording. Today we're going to talk about Redshift and its feature called Redshift Spectrum and the type of dedicated instances called RA3. So essentially, we need to go deeper about Redshift to understand what to do here in the architecture. In terms of architecture, Redshift is a scale-out architecture with auto-scaling associated, and it's designed to be 24/7, and your pay per second. You can turn off the cluster and be billed for exactly what you used, but essentially by design, it's for 24/7 over use cases, 24/7 use case. Spectrum is essentially a feature inside Redshift that allows you to process data on S3 and you pay as you go, $5 per terabyte. And the storage is typically stored as columnar storage. The architecture is active passive, meaning you have a kind of a load balancer, which is the leader node, which has an active server and a passive server with a read replica, so you're always on. Essentially, if a failed machine, say if you run into a failed machine scenario, you have a failover and everything is fine. The more nodes you have, the more you are distributed data. Essentially, 3 machines, 30% of the data on each machine, everything is backed up. So if one fails and all the data is rebalanced. The problem with scale-out architecture, generally speaking, is that when a disk fails, or even if a disk is not failing, if the data is not evenly distributed, then there's lots of shuffling between the nodes. So imagine a scenario where you have not 3 machines, 3,000 machines, and they constantly spend time on sharing their data with the rest of the cluster. Essentially, it's a challenge. It's a challenge that has, essentially, it's a challenge that has a bottleneck in your architecture, and you need to be aware of that. So you should prefer as less machines as possible, as we discussed. Shuffling on 1 terabyte worth of data is dependent on the bottleneck of your network card. So if you have a small machine, usually you'll get a weaker network interface card, thus slowing you down on the shuffling. Another issue is the upload time. When you use RA instances, you can have an advantage of using local disk, which is decoupled from the compute instances. So essentially, uptime and rebalance and scale up and down can be shortened compared to legacy nodes. If you use Redshift Spectrum, you can use the cluster's network capacity throughput to scan data directly from S3. Here, if you're using local disk, as discussed, you need to keep at least 2 petabytes worth of data. So you'll have a 50% disk space and not 100%. Is this slide clear? Okay. Generally speaking, when you want to upload 1 petabyte, assuming a 10 gigabit network interface card, essentially 1 petabyte means this amount of gigabits divided by 10 gigabits divided by 360 seconds, 3,600 divided by 24 hours. It's about 74 days to upload 1 petabyte. So essentially it's time consuming, and you should be aware of that. It's a challenge, it's bottleneck. Upload time on Redshift Spectrum is essentially 0. All the data is stored on S3. So it's an advantage. So let's talk about a question. Assuming the use case of 1 petabyte on S3 and you have an external table called tExternal, 1 table, 1,000 rows, and one of the columns is called user ID, and you're using Redshift Spectrum. I want you to guesstimate, meaning guess an estimation, how much time it will take you to run, select, count, distinct on user ID. Anyone?
The full table scan, isn't it? Because of the distinct.
Yes, but with one clarification. You have 1,000 columns, so essentially you're doing full column scan.
If it's partitioned, if the data in S3 is partitioned already using Spark-8, the user ID, I think that this query should run reasonably fast.
Right.
Yeah, so you don't have to scan out the columns.
And if it's not partitioned, because someone forgot to partition this specific column.
It will have to read the sequential, everything, right?
Yeah, so let's talk about it. Let's say 1 petabyte is 1,000 terabytes. 1,000 columns, so let's assume it's distributively evenly distributed, meaning 1 column becomes more or less 1 terabyte. So essentially, to read 1 terabyte, it's not partitioned. All depends on the type of cluster you have and how the data is distributed between them. Correct?
Yeah, a rough estimate might be the same 72 days that you mentioned for entire petabyte upload. If we take the same network speed and divide by 1,000, since 1,000 columns, that kind of will be the read, but that's probably not very accurate.
So let's assume you have 1 terabyte essentially divided to 3 machines. That means you have about 333 gigabytes per machine, and your disk space, let's assume you can read write 1 gigabyte per second. So essentially, you will be reading 333 seconds, which is essentially 5 minutes. This is a naive answer, obviously, but the idea is that you'll get a sense of the correlation between the server specs to your workload. Is this calculation clear?
It makes sense.
Okay, let's move on. So, second question, if you're using 1 petabyte of local disk, not external, same table, 1,000 columns, same concept of select, count, distinct, only this time it's local disk. We answered about the local disk, so let's go back and assume the data is stored on S3. So what would be if here the bottleneck was the read speed from the local disk, what would be the bottleneck here?
Network.
Network, obviously, yes. So it essentially boils down to the network speed of each node. So let's assume you take the most powerful machine and you have a 50 gigabit network card. So what would be your speed? In theory, what amount of data can go through the
Yeah, in
machine
theory,
per
it would
second?
be maximum 50 gigabit per second, but I'm thinking that S3 might have also their own limits on the storage, so depending on what they're using for the underlying storage, so it might be slower, but yeah, like in theory, 50.
Yes, just a naive answer. Good, you're absolutely correct. So essentially, you want to be having more machines because S3 is designed for parallel read, and you can essentially achieve any throughput you like, the more machines you have. However, as you mentioned, the underlying hardware might be bottlenecks and the network might be bottlenecks. So essentially, it's a balance. But the all in all, naive calculation is simple and you got it right. So I gave here a basic answer describing what we discussed, nothing too fancy. Let's talk about distribution. Redshift has a mechanism called distribution of data. Essentially, you can tell Redshift, listen, every node must have a copy of my data. So essentially, if I upload 1 petabyte, then I have 3 machines, I have 1 petabyte per machine, in total 3 petabytes. Why is that good? In which scenarios? Let's talk about this. Can you guess?
Availability, and I guess you can also split the workload if you want.
Split the
But
workload
yeah, first availability.
And avoid which kind of a scenario? Shuffling.
The one that you had before where disk is going down, yeah.
Yeah, good. Okay, so let's talk about evenly distributed. What happens when we distribute evenly?
You mean like 33% of the data per host? It comes to the
Yes,
same
when
thing.
you
If one goes down, you lose 1/3 of the data.
yes, essentially when you have one powerful array, the workload is divided into 3 machines, and each machine can do 30%, 33% of the calculation, essentially making it faster. Very good. So the pros of using Redshift: 24/7 flat rate, no surprises. Spectrum allows you to aggregate zettabytes of data, which is a lot. The Postgres syntax, which is usually good when you have a Postgres operational DB, and it's very fast if it's properly configured. The cons: legacy architecture, very costly, not flexible, scales very slow, vacuum is required, no semi-structured syntax, non-trivial to configure distribution keys, and there's a penalty for insert time. Oh, there's a question by Leo. Wait, 1 second. Leo was asking a question. For those who are not familiar with Redshift, can I ask about how the data is loaded from S3 to an SSD disk? Yes, it's a simple insert syntax. Like any other database, you give it a path from S3 and it's loaded directly to the local disk. The leak problem, as we mentioned in the beginning, most technologies have a problem when you have a very large volume. The time it takes to complete the query oscillates, essentially growing exponentially. Sometimes it handles it, the technology can handle it, sometimes it cannot. So essentially, there's a point here somewhere in the middle called the knee, where everything inflects, turns around, and becoming more slow and more likely to fail. So Redshift, by design, has this problem. In terms of response time, it's relatively fast, it's properly configured, but usually most people don't configure it properly. So all in all, the performance for the decent engineer would be very low compared to the competition. You need to work a lot to make it higher. Best practices, you should try to use internal storage. It works best. And have a dedicated cluster per use case. Don't combine workloads, simply because it has a concurrency issue. Questions before we go to the TCO analysis?
For Redshift, I think the AWS has released a serverless version of Redshift.
Yes.
And also
Yes.
dedicated clusters. For this particular use cases, should we go with the dedicated clusters that which we own that cluster because the people are constantly using it, or
Yes.
should we try the serverless Redshift?
Yeah. Serverless is for unknown workloads, unsteady workloads. When the use case is known, you're more cost effective to use 24/7 clusters.
Okay.
Thank you for your question. So TCO analysis. The numbers here, I don't want you to take them for granted or even as accurate or even right. You could assume they're wrong. It's simply for a matter of exercise for the purpose of these lectures. I created some sort of TCO analysis, total cost of ownership analysis that will give you a rule of thumb of how expensive or inexpensive the technology is. Essentially, when you upload, given our use case, we are uploading the data to S3, and it's about 200 terabyte compressed, so it will be about $4,800, which stands for about $60K yearly. We're going to need internal storage of 1 petabyte, which is essentially 2 petabytes, as we mentioned. And that would cost you an additional $600K. There's no special licensing. Assume you're not using Redshift Spectrum here. You should ask me why later. And there's no flat rate to go with it except for servers. For the sake of purpose of this training exercise, I chose RS3 16 extra large, 8 of them, which consist of 48 CPUs and 384 gigabyte, quite powerful and dense machines. This gives you a rule of thumb of give or take 16 CPUs per query. In terms of support, I guesstimated about 2,500 per user. Again, numbers may significantly be different depending your commercial agreements. But just to have a number here, you need about 30K, and essentially it totals up to $1.6 million per petabyte.
I understand that this is just for the use case, but in reality, we don't really have to load that much data into Redshift. You know, the purpose of loading data into Redshift is primarily for faster analytics. We could leave the data in S3 as much as possible, only load the data, the critical data that we need faster analytics into Redshift. So we could minimize the cost significantly by doing this hybrid approach. Does it make sense? Or I know you're
very happy you mentioned it. This is because of the ask me why question. What you're saying is essentially, let's keep the data on S3. And let's use Redshift Spectrum to use pay-as-you-go and run queries on top of S3. But the thing you're missing here in the TCO analysis, one second, please. Ken, let me know. Bye. The thing you're missing here is that in order to utilize Redshift Spectrum, you need a powerful cluster such as this. Otherwise, you won't be able to process 1 petabyte using Spectrum.
I see.
So essentially, all you save is this part, which is for the internal storage, but you can't save the entire amount because you need about at least half a petabyte, if not 1 petabyte worth of temporary calculations. So in a sense, you're correct, but it's not even theoretically correct. In theory, you need to have this at least. You can optimize maybe the cluster size, storage size a little bit, but you need to spend on 24/7 cluster when you're using Redshift to analyze Spectrum, unfortunately.
Yeah, unless you go with Athena.
Yes, but Athena is not designed for petascale. This is partly why it's not in this conversation. Does it make sense, guys?
Yeah, for this use case, it's perfect. Yeah, it does.
Okay. I think this is a good moment to stop because it's quite a long lecture, and I don't want to kill you with too much information. Is that okay with everybody?
Yes.
Yeah.
Yes.
Okay, my friends. Then we meet next week same time. And if necessary, we'll add more and more lectures. I think by next time I'll pick up the Slack, where, as we know this, it's about 20 to 30 minutes per technology. So we'll cover the rest of the 3 technologies, and we should be okay. If not, we'll make another session, okay? We have 2 more sessions, so bear with me. And if you have feedbacks or comments or questions, please, please, please send it to me. So to wrap up, in terms of assessment of our framework, faster, cheaper, simpler, Redshift is fast, it's not simple, and it's not cheap. Summary, our framework, faster, cheaper, simpler, we have an architecture. We need to assess all the different aspects and all the different challenges and all the different bottlenecks to properly select the technology and configuration. I'm not gonna bother you with the questions because we did a lot of questions and answered, and we covered basically everything. But in the end of the day, data engineering, it's all about the framework of faster, cheaper, and simpler. And you're more than welcome to visit our website for past content and participate in any way you want. Subscribe to the YouTube channel of Big Data Demystified. I will be honored, especially if you like the content. You're more than welcome to stay in touch via LinkedIn, website, the international meetup, or the YouTube. That's it, folks. Okay, I would like to say thank you very much and see you next time.